So here's my second example of proportional control for obstacle avoidance on Rosie-bot for today. The previous video showed how we do it with speed, where as an obstacle gets closer, Rosie-bot moves faster. This example shows that as an obstacle gets closer, Rosie-bot moves further away. Also an example of proportional control, where proportional to how close something is to Lily, the more she wants to get away, so the further back she moves. And this is also called proportional control or potential fields navigation, where the potential field is based upon a vector that is being pushed away. So please watch and enjoy.
So this video assumes that you have already watched the motion control and the bang bang avoid obstacle videos. So we will only highlight the additions to the code based upon creating a proportional controller for obstacle avoidance. So the first thing you should notice here is that we have some new variables, including max distance, amount of time the robot will move, robot speed set at 255, proportional speed and proportional distance both set to 0, and then 1 second, 2 seconds wait time, which are time delays for robot movement, as well as a state variable. Then in the loop function, the first thing we're going to do is we have a for loop that increments from 0 to 3 to read each of our sonar. And then after we read the sonar, we need to scale the value to be proportional to the obstacle. So if the distance is less than the maximum detect distance and greater than 0, then we set the bit state to a 1 to indicate that there was an obstacle there. And then we calculate our proportional distance, which is based upon the max distance times 1 minus the distance detected divided by the max detection value. And then we print out the robot distance to make sure that the value is in line with what we want it to be. And we then use that value to come up with the proportional speed that the robot should move based upon the detection distance. If there is no obstacle, then we just clear that state value, and then there is no change. Next, we use our switch case statements in order to move the robot proportional to the obstacle. So if there's a front obstacle, the robot's reverse speed as well as the delay are proportional to the value of the obstacle. If there's a back obstacle, the robot's forward speed and delay are proportional to the obstacle. If there is a left obstacle, the robot's spin speed as well as the amount of time it spins is proportional to the distance to the obstacle. Or if there's a right obstacle, the robot's spin time and delay are proportional to the distance to the obstacle. And this is how we do proportional obstacle avoidance with speed on our Rosie-bot.
So notice here when there's no obstacles, Lily is just sitting there. Then as I put up an obstacle, if the obstacle is really close, her move distance is in the hundreds going to 200. As the obstacle moves further back, her move distance gets smaller and smaller until she doesn't move at all. Let's see what this looks like on the robot. So no obstacles, really close obstacles. So Lily moves a lot. And as my hand moves back, the move distance gets smaller and smaller, proportional. Then outside of 5 inches, it stops.